Thanks. So today we are going to do polynomials. Is my screen visible?
Yes.
Okay.
Yes.
Yeah. So these are the buffer problems. You can take a screenshot of these before. Okay. Yeah. So let's start. So polynomials are like denoted by generally denoted by p of x, and it is like an expression of the form. It is an expression of this form. Here AIs can be integers, rationals, reals, or complex numbers. And one condition we here have is that an is not equal to 0. Because if like an equals 0, then we could have just started from x raised to n minus 1, right? Yeah, and here we define the degree of a polynomial as the number n. This number basically. So that's the degree of the polynomial p. Yeah, so basically, these are the main things about a polynomial are its coefficient, its degree, and its roots. So root is basically if p of alpha is 0, then we say that alpha is the root of p. And it should also be fairly obvious to see that if p of alpha is 0, then x minus alpha is a factor of p. Um, and somebody tell me one. Okay. If we have two polynomials p and q, then we can say that p is some aq plus b. Basically, this is just like Euclid's division lemma, but with polynomials. So here P and Q are two polynomials, and there exists unique polynomials A and B, such that P can be expressed as AQ plus B. And here degree of B is strictly lesser than degree of Q. Yeah. So from this, if we say that P of x is some x minus alpha times Q of x plus R of x, yeah, so P can be expressed as this. Now to show that x minus alpha divides P of x, we'll have to show that R of alpha is 0. But we can just do by substituting x as alpha. So we'll have P of alpha equals alpha minus alpha. This would just go to 0 plus R of alpha. So this implies R of alpha is 0. And so x minus alpha divides P of x. I hope this is clear. Yeah, so after these, we like see Vieta's relations. Actually, let's do a problem before doing Vieta's relations. Yeah. So this is a problem. This is a very famous problem. Like I think some of you might have seen it, but I'd like you to try this for a while. If you have any ideas or approaches, you can tell me.
We can use the roots of p, like if we have alpha being p of a root of p of x, there
Okay.
is also a root of p of x I mean p of x square.
Um, just a moment. So let alpha be a root of p of x. So we have p of alpha is 0. Okay. Then,
Then p of alpha square is also 0.
yeah, that's right. P of alpha square is 0 as well. So you can see like you can keep on forming roots from this. From alpha, you get that alpha square is a root. From here, you get alpha raised to 4 is a root, and so on. You can keep on forming new and new roots. But there is this thing known as the fundamental theorem of arithmetic. Sorry, fundamental theorem of algebra. Um, I'll just state that once here. Yeah, so this basically states that a polynomial p, like if polynomial p of x has degree n, then it has exactly n complex roots. Exactly n complex roots. Like the roots can be repeated. Like one root may occur multiple number of times, but there are exactly n complex roots. So clearly, a polynomial cannot have unlimited number of roots. It has the number of roots equal to its degree, right? So here, after a point, the alpha square, alpha raised to 4 has to kind of cycle back to one of the roots that has occurred previously. It can't keep on generating new roots, right? So can someone tell me what to do after this?
uh, we can always generate like roots bigger than the previous one. So like this is a contradiction. Like this does not work
Uh,
out.
in which cases can we generate roots bigger than the larger previous one?
Like from this only,
No,
alpha, alpha squared, and alpha to the power 4
it's only if
plus.
alpha is greater than 1, right? If it's less than 1, then
Yeah,
square will be smaller than.
yeah, precisely. Oh. So if alpha is greater than 1, then if you consider this sequence, this is like strictly increasing. This is a strictly increasing sequence. So you are getting new and new roots, right? So that's a contradiction because in this way you can generate infinitely many roots. So alpha can't be greater than 1. So let's say that alpha is less than equal to 1. Then how do we do? Oh, I mean, what do we do? Okay, in a similar way, if like alpha is
Oh,
uh,
alpha minus 2 is also a root.
yeah, good. So we had wait, what was it? Right, so we can put x as alpha minus 2. In this way, we would get p of alpha minus 2 times p of alpha equals p of alpha minus 2 square. This is 0. So alpha minus 2 the whole square is also a root. Right. So we can generate roots. So we can from alpha we can generate two roots, alpha square and alpha minus 2 the whole square. So how can we bound this? How can we what constraints can we put on alpha so that it can't be able to we can't be able to generate infinitely many roots?
Alpha should be 1.
Yeah, that's right. But the thing is, alpha can be a complex number as well. If alpha wasn't reals, then one would be the correct thing. So an accurate statement would be mod alpha has to be one, right? Where alpha is a complex number. So because if mod alpha is greater than 1, then this would keep on increasing, and if mod alpha is less than 1, then this sequence would keep on decreasing. So in either case, we are getting new and new roots. So that's a contradiction. So mod alpha has to equal 1. But that's not the, like, uh, what do we do then?
It has only one root, so the polynomial is linear.
Sorry, can you repeat?
So it has only one root, which is alpha. So polynomial is linear.
It
No,
can be 1 or minus 1.
no, it can be any complex number
Oh
lying on
shit,
the unit
complex.
circle.
Yeah, yeah.
Yeah. Okay. So see, the mod alpha is 1. That means that if we draw the complex plane and the unit circle, alpha can be any point which lies on this circle. And alpha, alpha square, alpha 4, alpha raised to 8, we won't be do anything. We like this sequence won't help us further. But what we deduced right here was that alpha minus 2 the whole square is also a root. Right. So alpha minus 2 the whole square also has to lie in the unit circle. So mod alpha minus 2 the whole square also has to equal 1. But like you can intuitively see this that this is not possible if alpha is not 1. Or you can also like formally prove this, like just say alpha is ai plus b, then yeah. I mean, if you simplify this, you'll just get that this can't be 1. I won't go into the details. So basically, from here, we can just get that alpha has to equal 1. Alpha cannot equal minus 1 as well, because if it is minus 1, then alpha minus 2 the whole square would be a minus 9, which is not possible. Basically, we got that all the roots have to be lie on the unit circle, and from there, we can reduce the value of alpha. So we can get that only alpha equals 1 is possible. So p of x is c times x minus 1 whole raised to k. K is any natural number here. Um, it can be 0 as well. Actually, it can't be 0. K is any natural number. And when we substitute this back into the original equation, we will see c square times x minus 1 whole raised to k times x plus 1 whole raised to k equals p of x square, which is c times x square minus 1 whole raised to k. So here from this, we just get that c equals c square. So c can be 1 or 0. So the solution set for p is um, yeah. This is a these are the solutions of p. P of x is 0 or p of x is x minus 1 whole raised to k. Does anyone have any doubts or something to say?
Why is K non-zero?
Sorry.
Why can't K be 0?
K can be 0, but if like, oh, it's my bad. K can be 0. It is positive integers including 0. Is everyone fine with this?
Yeah.
Okay. Now we'll see Vieta's relations. So this is basically a relationship. This is a relationship between roots and coefficients. How you can relate the roots and coefficients of polynomial. So this is very helpful when you want to change your view of looking at a problem. You can look at a polynomial problem both through its roots or through its coefficients. You'll see what I mean. So if p of x is summation, I'm just writing this in a summation form, and this is also some c times. So we can write p in both forms. The first one is the general form as stated before, and the second one is the form we got by fundamental theorem of algebra. Basically, there are n roots, so these alpha i's are the roots of p, and so we can write p in this form as well. Now, here we want to find the coefficient of some x raised to k. Right. From the LHS, we have established that the coefficient of x raised to k is of course ak. Yeah. But from the RHS, we want to find the coefficient of x raised to k. So how will we do that? Can someone tell? Or what will it be? Just say what it is directly.
We can like choose k x's from each bracket
Hmm.
and then find like
Yeah. So to find the coefficient of x raised to k from each of these terms, you need exactly k x's, and all the from the rest of the terms you take the root, right? Yeah. So if you see, if you take x raised to k times, what will you have is each term here would be the product of the remaining n minus k roots times c. So I can take c outside as well. So this is the product of the um yeah, it is the sum of products of all the combinations of n minus k terms. So basically, the notation we use for this is known as sigma. It is also called as symmetric sums. So basically, sigma one is I'm just writing it down. In the sigma nth term, there would be something in the power of minus one. Could you tell me what that would be? So basically, if you see, the minus term here is alternating. That is happening because, see, in the roots we have negative sign, right? So when we took k x raised to k terms, then we multiplied the remaining n minus k terms. So that would have had a 1 minus 1 raised to n minus k term with them for x raised to k. So here we have sigma n. So what would be the power, what would be the power of minus 1? Okay, we can just write this as minus 1 raised to n. Because see, the negative sign is repeating, right? So it will just be minus 1 raised to n here. Anyways, moving on. Let's do another problem. Yeah. Try this problem. I'll give you some time. If you have any ideas, you can tell me.
Oh, okay. We can like define a new polynomial for this one.
Sorry, what?
Uh, like taking the RHS in the first equation to the LHS.
So sorry, I didn't get it.
Okay. We can define a new polynomial Q of
Mm.
x.
Yeah.
That is P of x minus K upon K plus one.
P of x minus. Okay, minus. Okay, okay, yeah, sure,
Yeah. So this polynomial has n plus one roots.
sure.
I guess we can just put n plus one in this one and get the
Oh,
result.
wait, just a minute. It doesn't. It need not have n plus one roots. It won't have n plus one roots because the degree is still n, right? The degree of p is n.
So like they are it is zero on like for k equal 0 to n. Is it?
Just a minute. No, it's not zero for. Wait, give me just a moment. Okay, yeah. So for k equals 0, 1 to n, q of x is zero. Okay, yeah, fine.
So those are the n roots, right? For
Um, yeah, okay.
So maybe we can now like substitute n plus one, get something.
Oh, wait, give me just a moment. This doesn't make sense. Give me just a moment. See, like the degree of p is n, right? Here, you considered the polynomial q of x as p of x minus k upon k plus 1. What is k here? Is this x? Are you saying that q of x is p of x minus x upon x plus 1?
No, okay. Like this, I guess we should write down what it really is. Like p of x minus zero.
Um, yeah, go on.
Okay. So we will do the same thing.
Yeah.
P of x minus x upon x plus, okay, this we will define this using x.
See, here we have that P of k is k upon k plus 1, right? If you try to replace k by x, then you have an x plus 1 in the denominator. That's not ideal for a polynomial's definition, right? So you want to somehow remove that denominator. So what would you do for that?
Did I change the domain of that?
No, no, no. The domain has nothing to do with it. You can't define
So
a polynomial p of x if there's an x plus 1 in the denominator. Earlier you had said that q of x is p of x minus x upon x plus 1, right? You can't define this.
okay, we can write down like p of x minus k upon x plus 1, and like for each k we can write that down like from k is from 0 to n. I
Sorry, could you
think.
repeat? P of x is, sorry, what is q of x?
Okay, so for q of x, if we like do p of x minus k upon k plus 1, then if
Minus
we,
pk.
no, like only k upon k plus 1, then we, if we take like or write out all the values of k from 0 to n.
So are you considering n plus 1 functions of q here? You would have to mark it something like
Yeah,
qk. Okay, okay.
if we write like x equal to 0, then we have, eh, okay, not 0, like we can write anything from 0 to n for x here. If we write n for x, like q of n, then we have p of n minus n upon k, n plus 1, which is a root.
No, no. You see, if you put x as n, it wouldn't change k. K is not x, right? Is kx.
Oh yeah, it won't change that. Yeah, yeah, got it.
See, so your idea was not wrong. I mean, the thing is that there is a k plus 1 here, right? So you want to get rid of this denominator and then define a new function. The idea of defining a new function is absolutely correct.
Can we multiply
So multiply with one thing.
the entire thing by k plus 1? So um, it will be a polynomial then.
Okay. What are you saying to multiply with? X plus 1.
Yeah, yeah.
Okay, sure. So you have that q of x equals x at x equals 0, 1, 2, so until n. I think it is more beneficial if you just put a minus x here, right? Oops. So then we would have that q of x is
0. Yes.
q of x is 0 at, so we just got that 0, 1, so until n are the roots of q. So, and also we can check the degree, that if the degree of p of x is n, then the degree of q of x is n plus 1 here. And there are n plus 1 roots. So these are the only roots of q. Exactly these roots. These are the exact roots of q. So uh, q of x is just cx x minus 1 dot 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 till x minus n.
Yes.
Yep. After this.
Oh, how did you conclude this? Like QX is this. There can be a double root, right?
There can't be a double root because we have exactly n plus 1 values at which q is 0. And the degree of q is also n plus 1. If we had lesser number of values at which q was 0, then there was a chance of double root. But we have exactly n plus 1 values, so there can't be a double root.
Okay, got it. Okay, and now just substitute in plus quantity.
Sorry.
Or like now we'll like write substituting n plus 1 equals k work.
Uh, what? Sorry, could you repeat? N plus 1 equals k.
No, 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 never mind. Sorry.
Okay, so now we have represented q in like two forms. One is this one. I'll write this as like equation 1 and write this as equation 2.
Can we equate them?
Yeah, exactly. That's the point. So make a good substitution of x such that they would get equated and like you will get something useful out of that equation. What would you substitute x as like a some constant value?
Oh, okay. Now like substituting x equals n plus 1 will work
Just
after equating that and finding p of x.
yeah, x equals n plus 1.
N plus 1.
Okay, let's see. So if we substitute x equals n plus 1, we'll have n plus 2 times p of n plus 1 minus n plus 1 equals c times what do we get here? N plus 1 the whole factorial. This is what we get.
But how do we take care of C?
Exactly. We will have to do something else for that. So we have to find c as well in terms of n. How do we do that? Okay, see. Here we have a term of x plus 1, right? So if we substitute x as minus 1, then the term of p would vanish, which is what we want because we want to find c somehow in terms of n. So we will substitute x as minus 1 in this equation. Let's name this as star. Mm. Yeah. So now we have that c equals 1 upon minus 1 whole raised to n plus 1 upon n plus 1 the whole factorial.
So
Yeah,
now
so
we
now
can,
we just substitute this one back here. So we would get p of n plus 1 is plus minus 1 raised to n plus 1 upon n plus 2. Yeah, this is what we get. So based on the value of the parity of n, the value of p of n would n plus 1 would change. Is this fine? Does anyone have any doubts?
no.
Okay. Yeah, so let's take the next problem. Mhm. Just so does anyone have any guesses for the answer? What would be the largest possible number we can have?
2n minus 2.
Yeah, that's correct. Now, could you tell me which are the coefficients which, regardless of which polynomial we'll choose, will always be positive in the square of p of x?
Leading and the last one.
So, sorry, could you repeat?
Leading and the last one.
Yeah, that's right. The leading coefficient and the last coefficient. Because after the square, the coefficient of x raised to 2n would be a n square, and the constant term would remain to be a naught square. These are clearly positive because we are given that it's a real polynomial. Right. So the largest possible number of negative coefficients, like the total number of coefficients after squaring are 2n plus 1, because the degree would be 2n. So then our answer is obviously um, less than equal to 2n minus 1 as of now. So it is intuitive to try and prove if 2n, try and see if 2n minus 1 is possible. So could someone please tell how to approach that? Okay, so if you want to see if 2n minus 1 is possible, let's just assume that it is possible, and then we would see if we can find a construction or get a contradiction. Right. So let's say that there exists a polynomial p of x, such that after squaring it, the 2n minus 1 of its coefficients, basically all the coefficients other than a n and a naught, n square and a naught square are negative. So if we just see the some of the first the terms we get, they are like can someone tell what would be the coefficient of x raised to 2n minus 1? I just squared this, the p of x term. The only way we can get x raised to 2n minus 1 is either from x raised to 2n times the constant term, or uh,
2an n minus 1.
yeah, like it would be yeah, 2n n minus 1. So yeah, Similarly, we can write the term for 2n minus 2. It would be now 2n minus 2 is n minus 1, 2 times n minus 1. So it would be an minus 1 square plus uh, yeah, so
2a in n minus 2.
right, 2n minus 2. Wait, what? Okay, true, my bad. Yeah, so this is the coefficient for this. Now see, we know that an square is positive, so we might as well assume that an is positive, because otherwise we can just consider minus p of x. It won't change the square term, right? So let's assume an greater than 0. So in the coefficient of x raised to 2n minus 1, we have 2an times an minus 1. And as an is greater than 0, and we assume that the entire coefficient itself is negative, we will get that an minus 1 is less than 0. Is this fine? Okay, I have to. Yeah, so an
So
minus 1 is. Yeah.
how did you get this? Like a n minus one is
Your voice was a bit low. Could you please repeat?
how did you get this result?
Oh,
A
okay.
n minus
Yeah, I'll repeat. I'll repeat. See, did you get why the first term is always positive? Like it's just an square, right? And an is real, so it
yeah,
has to be
yeah,
positive.
got it, got it.
So we just assume that an is positive, because if it is not, then we can just flip p to minus p. Pn square would remain to be the same.
Okay.
Yeah. So now consider the coefficient of x raised to 2n minus 1. So it is 2 an minus 1, right? And we assume that, like, we want to see if 2n minus 1 is possible. To see if this is possible, we assume that it is possible.
Okay, got it.
So this all the coefficients other than the first and the last are negative. So an minus 1 is also negative.
Okay, got it.
Yeah. Now here we have an minus 1 the whole square plus 2an times an minus 2. So here an minus 2 would also be negative by the similar logic. So you can see that we can just proceed inductively. So could you someone tell me like the general coefficient of a term x raised to k maybe? I don't know. Okay, x raised to k is not that great. Yeah, so the coefficient of x raised to 2n minus k would be yeah.
Summation of r equals to 0 to k,
Yeah.
n minus r into n minus k plus r, I think.
A n minus k plus r.
Yes.
Oh, wait, just a moment. Yeah, that's right. Uh, yeah, this is correct. So now to show that all of these, so from this pattern, it is intuitive to prove that all of the AI are less than zero, where I is not n or zero, right? So we are just proving all the AIs are less than zero as well. So we are proceeding inductively. So we have that an minus one is less than zero, an minus two is less than zero. So we can assume that from an minus one, an minus two, we can assume that an minus k is less than zero, basically induction. And from here, now this is, if I expand this, this is just we have assumed that all the numbers from an minus one to an minus k plus one are zero. Now we want to show that an minus k is zero as well. So to show this, we are just using induction. And now here note that all the terms other than this an minus k term are positive. Is this fine?
Yeah.
Right. So only we just have to consider this term, and here we already know that an is greater than zero. So to make this make the entire sum negative, we need that an minus k has to be negative because everything else is positive. So an minus k is negative. Thus, um, so till when will this induction last? Can someone tell that? Like when will it end?
K equals n.
No, we started from a equals n minus one, right? We are going downwards, n minus one, n minus two. Now we proved for n minus k. It will keep going on downwards. But it will keep on going on till a naught, right? By this logic, a zero. Is this fine?
Yeah,
Now, um, what do we do ahead? Like, can we somehow get a contradiction here?
yeah. We assumed a naught. Now we had a naught greater than zero, but we somehow proved a naught is less than zero. It does not work. So
No, we did not have a naught greater than zero. We had that a naught square is greater than zero. Basically, the constant term after squaring the polynomial. We had assumed that an is greater than zero because we could flip from p to minus p. So we don't have that a naught is greater than zero. But yeah, you are right. A naught has to be greater than zero. Could you prove? Can you prove that?
If you check coefficient of x, it's like 2 and not a1.
Precise. Coefficient of x is just um 2 a naught a1. A naught is less than zero. A1 is less than zero. So the coefficient of x has to be greater than zero. But that's a contradiction because we assume that all the coefficients are less than zero. Is this fine?
yeah, got it.
Yep. So we have proved that we have now we have got a contradiction for this uh 2n minus 1. So if I say that the answer is something m, then m has to be less than equal to 2n minus 2. It can't be 2n minus 1. Now can we somehow get a construction for 2n minus 2 or again prove that 2n minus 2 is wrong? It's not possible. We don't, I mean, I'll just reveal at this point that 2n minus 2 is the answer. So we have to find the construction for 2n minus 2. So how can I get a construction?
We
So,
can take a like simple quad, right? Take x minus 1 whole square.
hmm,
So it's 2, and when we expand it, we have two negative terms.
sorry, what? Yeah, we have one negative coefficient. Okay, so I'll just does anyone have any idea of how can we can find the construction?
Uh, we can take something like x to the power n plus
Yeah. Yeah.
some function plus let's say the constant k. So
X
if we
plus some
x to the n
function.
plus some let's say fx, yeah, which
Okay.
has degree at most x n minus 1 plus
Okay.
k.
Yeah.
If we square it, it will be like x to the power 2n plus fx square
Hmm.
plus k square. Uh,
Yeah.
so we basically make like x to the power 2n k square and 2x to the power n k. These things, these are the only things which are positive coefficients. So take like uh, fx common from the other three elements like fx square, 2fxk, 2x to the power n fx.
Wait. Just a minute. Could you repeat the last part? I didn't get it.
Right. So x to the power 2n, k square, and 2x to the power n into k. These three terms will be like positive and all the other terms will be negative. We are trying to construct such a thing.
Okay, sure.
And
So it's
like
raised to
fx
power.
square,
Yeah.
so we take fx common from the other three elements like fx square, 2x to the power n fx, 2fx into k. Take fx common. Yeah.
Okay.
Now like take k to be large and fx to be small with negative terms.
Fx as in you mean the coefficients of fx, right?
Right.
So do you mean like negative or the small as in like in the approaching zero from the left hand side or something like that?
Uh, it should be, yeah, epsilon tends to zero minus, I think, yeah.
Okay, yeah. Okay, fine. I'll write this as like
Right.
epsilon less than zero and like epsilon tends to zero. Okay. If you are not familiar with this notation, this basically means that epsilon is negative, but epsilon is like really, really close to zero. We can like move epsilon as per we want. Yeah, go on. Uh, okay, yeah. So yeah, this is. I think this is.
Gx is like like fx has small coefficients, right? So
Yeah,
the only thing it will matter in the sign, like 2x square plus fx plus 2k. This will ultimately be positive and fx will be negative. So their multiplication will be negative in total. So this
yeah.
terms will have like negative coefficients.
That's right. That's right. So all these terms will have negative coefficients basically because f of x itself has negative. So f of x into f of x would be like minus f of x the whole square. So it would be negative. Similarly, if we have 2x square, then again we are just multiplying each term by 2x square. It will the coefficients won't change. It will continue to be negative. And here in the rest of the stuff, we have these three terms: x raised to 2n, k square, and 2x raised to n k. So these three terms will have positive coefficients, and which is exactly what we wanted, right? Terms would have positive coefficients, and 2n minus 2 terms would have negative coefficients. So this is a valid construction. Um, if you don't like exactly get what this epsilon tends to zero and stuff is, then you can also like consider the construction as something like this. Here, m is like a very large number. It is sufficiently large. We can make it as large as per we want. So even here, if we like square p of x and c, then I would write it as m times x raised to 1 plus 1 minus. So here, this is again sort of the f of x Arithra was talking about. Both constructions are valid. It is the same basically. Yeah. So does anyone have any doubts? Okay, I guess everyone has got the idea. Now let's see. Okay, 15 minutes. I don't think we can do a. Okay, let's I- I'll um I'll do one concept known as Lagrange interpolation, and after that we can see if we can do one problem. We'll see. So Lagrange interpolation is basically, if you see, we had done one problem back there where we had like p of k equals k upon k plus one, and we had like, basically values as xi and yi, where p of xi equals yi for I is from 0, 1, so until n. Basically, we have n plus 1 such values of xi for which we know what p maps xi to. So if we have n plus 1 such values, given that the degree of p is n, then we can uniquely figure out what polynomial p is. There is exactly one polynomial that like um, it's basically a unique polynomial which can pass through n plus 1 such points. Yeah, I hope this is fine. So, does anyone know how we can find out what P is if we are given such n plus 1 points? Okay, so we can,
If the
yeah, go ahead.
value,
Yeah,
if the values in the polynomial.
you're, I can't hear you.
Uh, After like if the values in the polynomial, then if we divide by that something,
Uh, yeah, I'll just write it down. Wait. This is the formula for P if you are given like n plus 1 points. Oh, does everyone like I won't prove this because like the proof involves some linear algebra stuff which we don't want to get into right now. But does everyone get how like what I have written here?
Yes.
Okay, that's great. Yeah, so I mean this we won't do any problems which will involve this much today, but like yeah, this is in general helpful. So you should always remember this. Okay, let's. Is it fine if I extend a bit like 10 more minutes than the usual time?
Yes.
Okay, sure. So we'll do one more problem. Yeah, this is a nice problem. So I'd like to give you some 5 minutes to think about it. If you have any ideas or approaches, you can tell me. So here we want to prove that there are at most n integers, right? At most n integers. So what is the first thing that you think of doing after seeing at most 10 integers? You want to prove that at most n integers, there are at most n integers t such that q of t is t. When would this not be true? When there are at least n plus 1 integers, right? So you would assume, for the sake of contradiction, that there exists n plus 1 integers. I hope everyone's familiar with this notation. This is just for the sake of contradiction, and this means that there exists. Any ideas? So whenever you like here, it is specifically mentioned that p has integer coefficients, right? So whenever you see integer coefficients in most of the problems, you should first recall the thing that if p has integer coefficients, then a minus b divides p of a minus p of b for any integers a and b. This is like you should always remember this whenever you see um, integer polynomial problem. You should use this. Anyone, anything? So from this, what we can see is that uh, p of xi minus p of xj divides p of xi minus p of xj. Can someone proceed from here? Like, what does this motivate you to do? You know that q of x is p of x k times. I would write that as p raised to k of x. This basically means that p appears k times. So this just like we can keep doing this until we get like p of xi minus p of xj divides p raised to k of xi minus p raised to k of xj. Like this is not raised to, it is like p appearing k times. Yeah, anyways, so this is just q of xi minus q of xj, which is xi minus xj as we assumed above. Is this fine?
Yeah.
Yeah, but we also have that xi minus xj divides p of xi minus p of xj from the uh, lemma I stated. I mean, the proof of this is like fairly obvious. Like yeah. So combining these two, we have p of xi minus mod p of xi minus mod p of xj is mod xi minus xj, and this is true for all one less than equal to I. Right. So this is an interesting thing, right? The difference p of xi minus xj is the same as the difference of xi minus xj, and that too for all ij from 1 to n plus 1. So, like from this, it is not hard to see that where this is going. We can see that um firstly, let's focus on removing the mod. How can we remove the mod here?
Uh, is it like possible to, I mean, is it legal to like assume xi greater than xj to like remove mod?
Sure, you can do that. I mean, you can just like say x1 less than equal to x2 less than equal to so on less than equal to xn plus 1. But that wouldn't remove mod, right? You would just get mod p of xi minus p of xj equals xi minus xj. Sorry, xj minus xi. That wouldn't remove the mod of the LHS because you can't compare p of x and p of xj directly, right? You would have to uh like maybe sum something or something like that for that. Try basically summing stuff. Anything? Okay, so we'll try summing the whole thing. So we'll sum mod p of xi minus p of xj. Sorry. Xi plus 1 minus p of xi. Oh, sorry. 1, 2, n. Yeah. What will this equal from this? So basically, here we are trying to remove the mod, right? So as we put I as I plus 1 and j as I, we have this equals summation mod of xi plus 1 minus xi. But we just assume that xi is monotonously increasing. So we just remove the mod here. Is this fine? How we remove the mod and stuff? Is this fine?
Did we remove the mod of both the sides?
Yeah, see, what I did here is I assume that xi is non-decreasing. Basically, it is this thing, xi less than x1 less than equal to x2 less than equal to, so until xn plus 1, right? So if I take p of xi plus 1 minus p of xi, that equals mod of xi plus 1 minus xi. But xi plus 1 is greater than equal to xi, right? So we can just remove the mod right away.
Oh, okay, okay, got it.
Here, basically, I just remove this mod. It is only this sum, which is xn plus 1 minus x1.
Yeah, cool.
Yeah. So now what? So now we can again write xn plus 1 minus x1 in terms of p. So that would give us mod p of mod p of xn plus 1 minus p of x1, sorry. Now see what we have got. We have got an interesting thing here. See, so the star equation is basically mod of p of x2 minus p of x. Wait. Yeah. What can we say from this? Say we did not have the mod on the LHS. What would that telescope do? I mean, what would be the value of the sum on the LHS if we did not have the mod? If we just don't have the mod, then this is just summation p of xi plus 1 minus p of xi I from 1 to n, which is just p of xn plus 1 minus p of x1, right? Which is what we have on the RHS, but in mod. So the RHS is just mod of this. So which is the mod of the sum. Basically, we have summation mod alpha I equals mod of summation alpha I. I is from 1 to n. This is the triangle inequality. I hope everyone is familiar with this.
Yes.
Yeah, so in the triangle inequality, when does the equality hold? This is equality, right? Here we have got the equality case. See, generally in triangle inequality, we have that the LHS is greater than equal to RHS. But the equality would hold only when all of the alpha I have the same signs. If one alpha I has opposite sign of the other, it would like reduce the total value of the um yeah, like basically equality holds when alpha I have the same sign. Is this fine? I mean, do you understand this? Okay, I think you. Yeah. So alpha I have the same sign. Now what were alpha? Alpha were p of xi plus 1 minus p of xi. So this term for 1 less than equal to I less than equal to n has the same sign, right? What does that mean? So if you consider the sequence p of x1, p of x2, so on till p of xn plus 1, then this sequence is either non-increasing or non-decreasing. Is this fine? Because all of these are the same signs, right? By non-increasing, I mean that it is either remains the same or it decreases. It can't increase. Monotonously decreasing, basically. Mm. Okay, I hope everyone's fine. So now we are almost there now. How do we conclude from here? So earlier we had that mod p of xi minus p of xj equals mod xi minus xj, right? But now if we say that, then like we can assume one of these. So say that it is a non-decreasing sequence. Then we can just remove the mod here and say that p of xi minus p of xj equals mod xi minus xj. How do we proceed from here? If you see, we had also assumed that like xi is here we had said this also, right? So we can combine this. We can like use this here to get p of xi minus p of xj equals xi minus xj. We removed the mod basically now. Now we have the same thing but without mod. How do we proceed now? So now basically see, this is true for all 1 less than equal to I less than j. Sorry. j less than I less than equal to n plus 1. So can we directly say from this that p of xi equals xi?
Oh yeah.
We can, right? Because like for each difference, it has the same difference as xi minus xj. We have also removed the mod. So I mean, I'm not saying in a very regressive way, but it has to be true. P of xi has to be xi. And in the other case, if we consider non-decreasing, then basically we would have p of xi minus p of xj equals xj minus xi. This is just the negative. So in this case, we would have p of xi equals minus xi. Is this also fine? So basically, we get either p of xi is xi for all I from 1 to n plus 1, or it is minus xi for all I from 1 to n plus 1.
Can you repeat this like what it is?
Sure. So here we got that this sequence of p of xi's is either non-increasing or non-decreasing, right? So we assume that it is non-decreasing. Non-decreasing means that if I is greater than j, then p of xi is greater than equal to p of xj. So that means we can just remove the mod p of x because p of xi is already greater than equal to p of xj. So p of xi minus p of xj equals xi minus xj because we had also previously assumed that x's are non-decreasing. So we got that the differences of p of xi and p of xj are the same as xi and xj for all I and j for all j less than I, which has to imply that p of x has to be xi because like you take any two p of x and xj and their difference equals xi and xj, right? So it can't be anything else. Is this fine?
Okay, got it.
Yeah. Similarly, we have p of xi is minus xi. Wait, what did we have to find? Yeah, we want a contradiction. We have to prove that at most n integers suffice, right? Yeah. So can you help me find the contradiction now? We are almost done. What's the contradiction here? Come on, it's not that. See, in either case, you can just consider the polynomial q of x. This is p of x plus minus x, right? So in the first case, we consider p of x minus. Sorry, I should write this as um yeah. So in the first case, we assume p of x minus x, and in the second case, we assume p of x plus x. And this has n plus one solutions. But we know that p has degree n greater than equal to 2. So this whole thing also has a degree n. But we are getting that it has n plus 1 roots, which is a contradiction. Do you get this?
Uh, can you repeat the line you just said?
Yeah. Oh, okay, wait. I think this notation might be a bit confusing. So in the first case, where p of xi equals xi for I is between 1 and n plus 1, then we consider the function polynomial q of x equals p of x minus x. Can you tell me what are the roots of Q?
All I to X.
Yeah, all Xi's. So is that basically all Xi's, right? From 1 to n plus 1. But if you see, we are given that the degree of P is n and n is greater than equal to 2. So the degree of Q also has to be n, right? But we are getting n plus 1 roots, which is a contradiction. This cannot happen.
Oh, okay, okay, got it.
Yeah. Similarly, in the second case, we would our function polynomial would just be q of x equals p of x plus x. Just works. So we have a contradiction here, and this contradicts basically the assumption we had made on the very first line, which was that there are n plus one integers such that q of xi is xi, which cannot be true. So there are at most n integers t such that q of t is t as desired. Any doubts in this solution? This was a bit lengthy, I think. So if anyone has doubts, you can ask. So if anyone doesn't have doubts, so I guess that's it for today's class. If anyone has any like questions, you can ask. Wait, I'll just stop there.